computer because I don't actually know how to access the cloud. All right, so then real quick, I'll just go back. This is our finite state machine. I found that this kind of syntax here, the 4-tick D9, works better as it gets larger. For some reason, the Quartus compiler was giving me some problems with a 10-bit one-hot encoding like that. It was starting to get have issues, and rather than debug it, I just went with the 4-tick D syntax here. Remember that the D means decimal, so this actually converts to a 4-bit binary number representation of 9, for example. Then we were watching state. We're going through state 0 through state 9 and setting next state equal to the appropriate next state. And then on the clock edge, we are setting state equal to that next state. And that way we are also, we're outputting the transitionary state, that next state value, so we can use that. And we're also separating all the conditional logic from the sequential logic. So back to the state decoder then. We're watching our next state, and on the transition from one state to the next, we're setting our ALU operations. These X's are just don't care values. We just allow the compiler to not worry about setting them, allow them to be whatever they are. Right here, this is how I'm encoding my ALU operation. This is add, this one's OR, this one here is XOR, and that one here is not. And by setting these on the transition, I know that the operation on the ALU will have taken place before I open up D3. And that's the biggest thing. My enable signals are just a 6-bit vector. And my next state, these don't need to be 10 bits. These need to be 3 down to 0. 3 down to 0. 3 down to 0. My enable signal is 6-bit here. This is what they represent. 0 through 5 with the different buffer and our enable signals. And those are passed in the top level module. This is sort of the brains of the operation. Really everything that needs to change changes inside this module. Everything else is more or less a static operation. So let's keep going. We will look at our buffers next. So I'll look at buffer.v. To make a buffer is very simple. We set this in out port. This is going to be our output. And the reason why we're going to use the in out variable here is to tell the compiler that it's going to have multiple things writing to this IO port, and that is okay, because it's essentially what lets the compiler know that this is in fact a tri-state buffer. And then we have our dedicated write port. This is where the data that we want to write to the tri-state buffer goes. And then we have the enable signal. And then for the logic, we're just going to assign IO equal to write when enable is true, and equal to Z's otherwise, where Z is just high impedance. That's our buffer. Questions about any of this? Okay. Then we have our ALU module. And here I have A, B, and op. And I'm outputting a result. And all I'm doing in here is watching A, B, and op. And in the case that any of them change, I am going to switch across what op is equal to. And depending on the value for op, I'm going to make my result accordingly. And then for the default, I just said result is equal to A because you need to set it to something. So for the default, I just said, you know what, just let A pass straight through. All right. So then the last thing we need to look at before I go to the top level module, well, first, before I jump in, any questions about anything that's happening here? Okay, all pretty straightforward. That's what I thought, but I want to make sure. So when we jump into the top level module, no, last thing before I jump to the top level module is talking about registers. So I've combined all three of my registers into a single module. You don't have to do it that way. You can have separate R1, R2, R3 registers. That's totally fine. These are flip-flops. This is how you write a flip-flop inside of Verilog. Is you could say on the positive edge, this could also be the negative edge, or you could use a generate block like I showed last time, however you want to do it. But on the edge of enable, where enable here is a 3-bit vector because there are 3 registers. So on the edge of enable or on the neg edge of reset. If not reset, then I'm setting the output all to zeros. So this has its own reset. And otherwise, R1 out is equal to R1. And then again, on the positive edge of EN1 or the negative edge of reset, reset logic is the same. And otherwise, R2 out is equal to R2. And same thing for R3. This is all pretty simple. The only real difference between a flip-flop and a register is that the flip-flop happens on the edge. So the data is passed across the flip-flop only on an edge. So you need to make sure that you're always setting the enable signal back to 0 when it's not in use. Because otherwise it'll take 2 clock cycles because you'll have to set it to 0 and then set it back to 1 to trigger that edge again. So you can see what I mean by that if I come back to my state decoder for 1 second. And in my enable signals, anytime, for example, I've got a register set here, and then in the next state, I have it set back to 0. And that way, whenever I need to set it high again, whenever I need to enable it, I can do that just by flipping the edge. Okay. All right. And then the last thing is our top level module. And it's saying that FSM expects 11 bits, but it doesn't anymore. Oh, it still does. All right, fix that as well. This is 3 down to 0 and 3 down to 0. Save that. And same thing with our state decoder. Right here, it's getting the state once again 4 bits here. So I'll just put these together as state and next state. Like that. All right. So now I have my FSM that gets my clock as an input. It gets my reset as an input. It gets my state as an output and my next state as an output. These are defined up here. My state decoder receives state as an input and next state as an input and enable signals as an input or as an output, sorry, and ALU op as an output. In the ALU, A is equal to R1 out, B is equal to R2 out, op is equal to ALU op, which comes from state decoder right here, and result is equal to R3. So we're going to put the results from the ALU onto our R3 wire. Now we have our registers. The input for R1 comes straight from the data bus. The input from R2 comes straight from the data bus. The input for R3 comes from R3, which is the result of the ALU. The enable signals I'm passing here 5 through 3. The reset signal, and then it has R1 out goes to R1 out, R2 out goes to R2 out, and R3 out goes to R3 out. Those are our outputs. And then we have our buffers. I'm writing to our output buffer the value of R3 out, and I'm passing to it the enable signal EN2, and the IO, which is our output, it goes back onto the data bus. So this is R3. In fact, it is the case for all of the buffers that they go back onto the data bus. That's the reason they exist. Okay, then we have our immediate buffer, which is always going to be the value of 3. So I just put it in there. And that's just according to the lab handout. The enable signal, which I gave it the enable signal of 1. And those correspond with what I decided in my state decoder. And then again, it outputs onto data bus. And then external buffer, it receives external, which is right here, the 4 switches. And it gets an EN signal, EN0 in this case, and then it writes out onto the data bus. And then finally, BCD to 7seg reads from the data bus and writes to the 7seg display. Any questions about that? That's how this all connects together. This is just the Verilog interpretation of the diagram that we were given. Oh, we have a couple of chats. Sorry, I missed those. Okay. Yeah, we can. I'll unlock it. I'll let you know, Andrew. And okay, cool. All right, so I'm going to go to Canvas for a second so we can look at the lab handout. All right, here we go, lab 5. All right, so this is the diagram. So what you're going to do to set up your top level is just look at what's connected to what and make sure that everything that you have is connected the same way it's connected into this diagram. So for example, your 4 switches should go into a buffer, then the output should go onto the data bus. So you need to write that into your Verilog. We're going to ignore these try buffs here. We don't need them. But your R1 should be read from the data bus and should input into the ALU. Same with R2. So it's just a matter of thinking about how everything is connected and making sure that yours is connected the same way. Okay. And then I am going to quickly just walk through my FSM logic so I can show you how it relates to the state machine that we're given. All right, so at reset, it goes to state 0 and tri-states all the buffs, resets all registers to a value of 0. Okay, so this is reset. I set all of my enable signals to 0. That's what it means to tri-state all of the buffs. And the reset of the registers is taken care of by its own reset signal that's also connected to the button on the board, where it will set all of the values to 0 for me. Okay. In state 1, the machine reads the data on the external switches and loads it into register R1. So if I look at my state decoder, here we go. This is state 1. So I need to enable the external buffer and I need to enable the R1 enable switch. So if I look, there's my external buffer and there's my R1 enable. So 0 and 3 are both high. So that takes care of that. Okay. On our state 2, I'm going to load the integer value of 3 into R2. So that's pretty easy to do. I've already got 3 as being connected directly to the immediate buffer. So all I have to do is open the immediate buffer right here and enable R2 right here, which I've got immediate buffer, R2 enable. Cool. Then in the transition between 2 and 3, I set my operation to addition, so that by the time we get to state 3, I know that by the time we get to state 3, I know that the addition has happened. So R1 plus R2, and I can now store the results into R out. So in state 3, all I have to do is enable R3, and the results will go in. When we get to state 4, I need to transfer the data from R out to R2. So that's as simple as enabling the R out buffer and the R2 register. So there's the R out buffer right there. And there's the R2 register right here. Yeah, okay. Then in the transition between 4 and 5, I set my operation to be an OR, so that by the time we get to state 5, all I had to do is open up R out, and I know that R1 or R2 has been done. So state 5, I open up R out, and I'm good to go. Then in state 6, I move R out into R1. So state 6, I simply just open up R out and R1. Sorry, is that right? No, the output, let me double check. It says move R out into R1, so I need to open up the output buffer and R1. So this is R1, this is, sorry, this is the output buffer, this is R1. Yes, there and there. Okay. And then in the transition from 6 to 7, I set the operation to be not, so that when I get to state 7, I just open up R3 and allow not R1 to pass through. In state 8, I set 1 again, so I put R1 onto, sorry, R out onto R1 again, which I think is what it says to do. R out goes to R1. Cool. And then in the transition between 8 and 9, I set the operation to be an XOR. And so I end up with, in state 9, setting my enable signal to be 1 here to enable, to open up R3 to allow it to write. That's this guy. And then I also enable the data bus output buffer so that the final value gets written straight onto the data bus, so it can be written, so it can be read from our hex to 7 seg decoder. Are there any questions about any of that? Okay. So that's it for the things I have to show you. So at this point, I'm going to write a module for the hex to 7 seg display that will actually display a full hex value. And then we'll go from there.
Could you show the buffer and the ALU files once again? I just had one little thing I didn't catch.
So here's the buffer. Your in out here is required to tell it that it's a buffer. And then it's just IO is equal to EN. If so, then write. Otherwise, Z's.
If IO is 4-bit and N is just an input, how, like, what is that like checking for equality?
So this is a ternary. It should be 2 equals, by the way. Oh no, IO is equal to EN. Yeah. So all this is a ternary statement. So all it's saying is, if this is true, EN is 1, then IO is equal to write. Otherwise, IO is equal to 4 tick B Z Z Z Z.
Oh, gotcha. Yeah, I remember those from my CS specs. Thank you.
Yeah, no problem. Okay. Then the ALU is just A and B, both 4 bits, and an opcode, also 4 bits. And then we switch on the opcode and set the result accordingly.
For the 7 segment display, are you just gonna make, do you just have to make so it displays like A, B, C, D, E, F?
Yeah, that's all I'm going to do.
Okay, cool.
All right. All right, cool. Then I'll go ahead and stop the screen. Stop the recording here. I'll keep my screen up and you guys can feel free to ask me any questions as you're working.
What's the syntax for XOR again in Verilog?
It is the caret. So it's, we'll go to it. The ALU, the caret right here.
Okay, sweet.
Stop